This is Unit 4, Lesson 3, and we're moving on, but really not to new concepts. I really just want to review kind of this whole idea of switching back and forth between a Riemann sum and a definite integral, and also then pulling back into all this Lesson 1, the LRAM, MRAM, RRAM, and how now we're going to have to kind of realize that the integral is asking us to approximate that area. So on the first page here, it says additional learning resources, remembering the delta x term. So that's one of the most common mistakes when you're given a multiple choice question, or you're given a question to sort of match the definite integral to the Riemann sum, is to ignore the dx in the integral, which corresponds with the delta x term in the Riemann sum. When we're rewriting it, we need to make sure that we're correlating the dx with respect to x to those bases, the delta x's at the end. So given the integral from a to b of f of x with respect to x, the corresponding Riemann sum is the limit as n goes to infinity. And what happens here is that they're missing the delta x sub k term at the end. It says what is missing is the delta x term in the next sentence there, but let's add it to that summation. So you see the summation, you see the f of x, but you're forgetting to multiply by the delta x again. And the other reason I want to bring it up, besides it corresponding to the dx, remember, these are our rectangles. So the f is the height, and the delta x is the base. So in order to get the area, you need to multiply both dimensions, base times height. And they wrote it down here as the formula b minus a over n. Same idea, delta x is b minus a over n. So in the first couple of exercises, it's just having us look at the Riemann sum and kind of put back in that missing delta x term. So it says, try the following exercises. Each of the below definite integrals is correctly written as a Riemann sum, but the delta x portion is missing. Write the correct delta x term to make the statement correct. So notice it's the integral from 0 to 3 of f of x with respect to x. You could calculate your delta x using the formula b minus a divided by n. You could also see that, remember, delta x is going to show up in this x sub k term. The x sub k is a plus delta x times k. So delta x is always going to show up in the parentheses as well, so you might be able to find it there. So this guy is missing another 3 over n multiplied. For number 2, we've got the definite integral from 0 to 5 of g of x dx. They set up our limit as n goes to infinity of the summation g of 5k over n, but forgot to do times 5 over n. This time I really kind of just looked at that 5 over n is this term delta x times k. Notice that there's no number because a was 0 added to that delta x times k. So that's sort of why it's just the delta x times k, because we're adding a 0. Questions? That's really what this whole first page is. Take a look at number 3. It gives us this Riemann sum. The only thing that we're missing is our delta x at the end. And number 4, wasn't there a 4? Oh no, just a 3, sorry. All right, the next page kind of gives us an example of how maybe it could show up as a multiple choice question. It says the question below is followed by 4 student responses. 3 are incorrect and only 1 is correct. Select the correct answer choice but we're also going to identify the error in each of the incorrect responses, which obviously on a AP, you wouldn't have to do that second part, but for our notes, it's a good thing to do. So we're looking at the integral from 3 to 5 of x to the 4th with respect to x. I like to do kind of my calculations before I even look at the choices. So a couple of things that I want to know are delta x, so b minus a divided by n. So I know I'm looking for my delta x is 2 over n. And I also want to know, God bless you, what I'm plugging in, my x sub k. So x sub k is going to start with a because that's the beginning of our interval. So in this case, my a is the 3. And it would be plus my 2n times k. A plus delta xk. And if I have those two things written on the side, then I know what I'm looking for, because the limit as n goes to infinity, that's the same for all of these. The summation part from 1 to n, that's the same for all of these. So it's what goes in the parentheses and what's on the end that we have to look at. So let's take a look at choice A here. Inside the parentheses, they have 3 plus, well, they just have k over n. So we're actually missing a 2 inside the parentheses here, because it's delta x times n. And actually, on the outside, I'm also needing a 2 over n, not a 1 over n, because we have to multiply by delta x. So this one was incorrect. We should have had 2 in both of those places. Same thing with this one. We're missing the 2k over n. Has the right delta x on the end that time, no? All right, the next one has the 2k over n, but the wrong delta x on the outside. So it's not until we get student response D that we found delta x correctly inside the parentheses and outside the parentheses. And again, just kind of reminding you that it does show up twice is another important thing to do. Questions? All right, the bottom of this says, go back to student choice A and write the integral that they were really writing. So I'm going to rewrite it on here. It's the limit as n goes to infinity, the summation, k equals 1 to n. All of that is always the same. And then student choice A did 3 plus k over n to the 4th times 1 over n. So when you're going backwards like this, you want to figure out, first of all, what A is, and that's going to be the 3 that was added inside. And then you want to look at the delta x. Now, the reason why we can do student choice A is theirs was actually a valid Riemann sum, but just for the wrong integral. Their delta x, both inside and out of the parentheses, was matching 1 over n. So when we're turning this into a definite integral, we're starting at 3, and then the numerator of delta x is the total length of the interval. So we're just going to add that to get the b at the top. 3 plus 1 is 4. And then you could even just double check. 4 minus 3 over n. Yep, that's 1 over n. And then in our head, we're going to say everything in the parentheses becomes my variable x. It's something to the 4th power. So in the Riemann sum, it looks like a big old mess, but in the integral, it's just x to the 4th. And then our dx at the end, with respect to x, is corresponding to our delta x, or the base of our rectangles. Questions? All right, so the first day's lesson, when we did LRAM, MRAM, RRAM. Oh, that's weird. Where's the rest of my lesson? It asks us now, apply your understanding left and right rectangle Riemann sums. Now, in this first example, the reason why I picked this one is that I want you to remember that a Riemann sum doesn't always have to be equal subintervals. So you have to read the question to see if they're requesting that or not. So this one says, approximate each of the given definite integrals using the specified method. You may leave the answer in expanded form, so we don't have to simplify. You can leave it as a sum of the products. And n is the number of subintervals that they want you to use. But what I want you to note in this one is this example does not say equal subintervals. This example does not say we need equal delta x's. So with that said, notice there are some points that are defined there that would be whole numbers. Whereas if I were trying to look for maybe the y value at 1, that's, I don't know, 3.1, 3.2, I'm now approximating. So if they're not going to specify that I have to be equal, let's look at our first integral from 3 to 9. So we're trying to calculate this space here from 3 to 9 using n equals 3. So they want me to make 3 rectangles. And it's saying a left Riemann sum. So we're going to have to use the y values on the left side. So for the first rectangle, I'm going to use this height of 2, but I'm only going to make it 1 box wide. And the reason why I'm doing that is because I have a dot next to it that I want to use as my next height. And I want that to go over 2 boxes because that's then where my next dot shows up. And then my last one fits for 3. This still qualifies as a left Riemann sum, even though it's not equal subintervals. So the approximation for each is then base times height, base times height. So the base is 1 in the first one and the height is 2.
How did you know like where to put your lines? Like,
great question. The left side of the interval has to be where I get the height from. So each of my rectangles had to be drawn from the left side over. That's what's making this an LRAM. I didn't necessarily know where to put the heights since they didn't say it had to be equal. I chose to use their dots as the height because they were whole numbers and I wasn't then approximating even further. So I stopped at a width of 1, a width of 2, a width of 3 to utilize their dots. And then they said we don't have to simplify this. So after I wrote out the base times height, we can leave it just like that. So now with that said, look at the next one. The next one wants the whole interval from 0 to 9. So that's one part of this exercise to kind of pull out the interval from your definite integral symbol. But now they want me to make 4 rectangles using a right Riemann sum, which means when I draw the rectangle, I have to be starting on the right side and then drawing the height backwards. So if I look at my first interval here, my first dot on the right, if you will, is at 3. So I actually want to use that height and make my first rectangle using that dot. And I'm starting on the right side and drawing back to the left. Then I've got the next dot drawing back to the left like this. Then 6, 6, draw that back to the left. And then 9, 4, draw that back to the left. And I'll kind of just shade in these red ones so they stand out as the right side. Notice the height started at the right and then I drew it back to the left. So then base times height, base times height. The next base is 2, height is 6. Next base is 3, height is 9. It was only because this one did not say we had to have equal delta x's that I kind of went off the rails and made all different size rectangles, because we wanted to utilize the points that were explicitly defined for us, that we knew there was a dot there. If we were forced into equal delta x's, we wouldn't have had that choice. Josh. Which one, honey? The last one should be 3 times 4. Yes. Good catch. Other questions? All right. The next one, you see now definitely that I got this handout from the AP Classroom. I don't love the formatting of this. The first question here is dealing with the table. This is what I labeled as number 4 on our handout. And then this one is totally unrelated to the table. So let's just draw a line and we'll call that number 5. I don't know why they grouped it together in a table there. So number 4 says, the table below gives velocity value measures in feet per second every 4 seconds. And it asks us to approximate the definite integral from 0 to 16. So if we peek at the table, that's the whole table. And then notice there's another thing in here. We've got absolute value of the velocity. So absolute value of v is going to make everything positive. So I'm even going to just kind of add my own little row here that the absolute values are all positive. N equals 4 using a left Riemann sum. Now look at the table. The table is going by increments of 4, 0 to 4, 4 to 8, 8 to 12, 12 to 16. So those are the 4 rectangles that I'm going to make. The base then is that delta x. Delta x is increasing by 4 each time. You could even say that you could calculate that as 16 minus 0 divided by 4, because when they're equal subintervals, b minus a divided by n is where we get our equal delta x's from. Since it's right in the table, I didn't really have to write that out, but I just want you to see how it's all kind of connected. So now we're going to do the base of 4, and then they requested a left sum. So on this first interval from 0 to 4, I'm going to use the height on the left side because that makes it a left Riemann sum. So 4 times 12. The next base is between 4 and 8, and I'm going to use the height on the left side, so the 20. The next base is between 8 and 12, which is again 4, and I'm going to use the absolute value of the height on the left side. And then my last subinterval is going to use the height of 12. If you remember from the video for lesson 1, in an LRAM, the last y value of the table drops out because you're choosing the heights from the left side. So the rightmost one or the last one on the table is going to be the one that drops out. And then we would have to add this all up. Now, number 5, since it is not connected to the table, I also don't like that they didn't really clarify the question. So I'm going to write the question the way I feel like it would really show up on the AP. This question would really say, if f of x is a continuous function, approximate the given interval using an RRAM or a RRAM of 3 equal subintervals. That really should be what is written above this integral. Because like I was just saying, how do I know if I should be using equal subintervals or not? They have to ask for it. And in a question like this, where I really have minimal information given to me, they would need to say that they wanted equal subintervals here. So with that said, I would first calculate that delta x. B minus A divided by n, which is 3. So the equal subinterval is 8, and that's going to be the base of all of my rectangles. So setting up my RAM, I would have the base of 8 times, well, now I would need the height. And in my first subinterval, it would be from 0 to 8. So where should I get the height from if I want an RAM? The 8. So they don't tell me what f of x is, so I'm just going to write times f of 8. Plus the base is always 8, but now my next subinterval is between 8 and 16. We're pulling from the right side, so f at 16. And then the last one, we're going to use the rightmost, since it's an RAM, f at 24. And I couldn't go further with this because they never told me what f of x was. Questions? Tonight's homework is any questions at home before I move on? All right, tonight's homework is a Delta math assignment. And I want to just show you one of them. Remember that you do have the videos that you can watch to help you out, but a couple of the first ones are going to be the same review like you did last night, but the next one specifically, the graph ones, I want to show you one of them. So here's an example. It says, let f be a function graphed below. If 5 subintervals of equal length are used to draw rectangles whose area represents a midpoint Riemann sum, and then it gives us the integral from 2 to 7. So the first thing I want you to do is calculate delta x. So delta x for this one would be 7 minus 2, which is 5, and then divided by 5 subintervals, and that's what you're plugging in here, that we would have intervals of 1. And when you plug that in and press go, notice it sets up like these rectangles at the bottom of length 1. You're then going to drag it to make it the appropriate approximation. This one wants a midpoint Riemann sum. So I'm going to grab my midpoint. Grab the midpoint. Come on. I'm grabbing the wrong dot here. There we go. I'm trying to grab the midpoint. There it is. It finally went. I'm trying to grab the midpoint and drag the middle down. And then this one, I want to grab the midpoint. It's really weird that it's not grabbing exactly where I touch. All right, I've got how it's off. Grab the middle, drag it up till it hits the function, grab the middle, drag it up, and so on. If it said an LRAM, we would grab the left side and drag it up. If it said an RRAM, you do the right side. And what this exercise is supposed to do is to help you visualize each different one.